Hello everyone, welcome to this 17th lecture in the NPTEL course on Riemannian geometry. So we have already introduced notion of a connection on a manifold, and then we have discussed various locality properties. Then in the previous lecture we introduced this notion of parallel transport or parallel translation, and I demonstrated that the parallel transport, this parallel transport map can actually recover the connection, right. So today I want to talk about, I want to get back to, so far in our discussion of connections we really haven't mentioned the Riemannian metric, right. So today I again want to come back to Riemannian geometry and consider connections on Riemannian manifolds. So throughout the lecture Mg will be a Riemannian manifold. Okay, so the central notion is that of a Levi-Civita connection. Okay, so here's the definition. A connection nabla on M is called Riemannian, or what is much more common is called a Levi-Civita connection after the mathematician or geometer Levi-Civita. If it satisfies the following additional conditions. So satisfies two additional properties. So of course it satisfies the properties of being a connection, but it also satisfies the following two additional properties. One is metric compatibility. Okay, so this says the following: for all x, y, z, your connection must satisfy a certain product rule. So if you take g of x comma y, then that's a smooth function on M, so you can differentiate it with respect to the vector field z. Then that ought to be the derivative of x with respect to z inner product with y plus the inner product of x with the derivative of y with respect to z. Right, so this is completely analogous to being some sort of a product rule, okay. And secondly, we also need what is called torsion freeness. Or in other words, which I'll explain at some point in this lecture, we need the connection to be symmetric, okay. So that just means that for all x, y here, the torsion tensor, which is defined to be this, should completely vanish, should be identically 0, okay. So if a connection satisfies these two properties, it's called a Levi-Civita connection. Okay, so the fundamental proposition, in fact one can sort of call it the fundamental theorem of Riemannian geometry, is the following: that for any g there exists a unique Levi-Civita connection. Okay. Moreover, the corresponding Christoffel symbols also have an explicit formula. So gamma ijk is given by half G upper KL. So remember, G upper KL were the components of the matrix inverse times del I GLJ plus del J GIL minus del L GIJ. Okay. So the Christoffel symbols also have an explicit formula in terms of the metric. So this also shows to you that the metric completely determines this Levi-Civita connection in a unique way. Okay, so we first prove uniqueness. And then we will prove existence. Okay. So for any vector fields x, y, z, we have the following: x applied to g of y comma z by the metric compatibility condition or the product rule, it has to be this, right? Similarly, y applied to g of x comma z has to be g of nabla y x comma z plus g of x comma nabla y of z. Similarly, z applied to g of x comma y has to be g of nabla z x y plus g of x nabla zy. Okay, so now using the fact that the torsion is 0, I try to combine these. So for instance, I can add the first two and subtract the third. Okay, and I end up with the following. So you can do the algebra on your own. For now, you can sort of trust that I have done the algebra carefully. You end up with the following formula. So 2 times the metric, the inner product of nabla y with respect to x comma z is given by this long formula. Okay, so I'll denote this formula by star. So the thing to notice is that the RHS does not have a nabla, does not have the connection terms at all, right? So then if nabla tilde is another Levi-Civita connection, then what you have really shown is that g of nabla xy comma z is the same as this, and this happens for all z, all vector field z. But then because the metric is non-degenerate, this implies that these two connections must be the same. Okay, so that proves uniqueness of the connection. So as soon as you have a metric compatible connection which is symmetric, then it has to be unique. Okay, but on the other hand, star establishes also existence because G is non-degenerate. If if I know exactly what these are, so so in other words, if you take comma this is clearly a one form, right? So given any z, you evaluate the inner product of nabla xy comma z. But now remember we had the sharp operator, which was an isomorphism between the space of one forms and vector fields. So just apply the sharp operator to this one form. Okay, so we now have a formula for this connection. Okay, and the point is that this one form here is given by this RHS, which does not involve the nabla at all, right? So you take this entire RHS, that will, if you vary your z, that will define a one form on your manifold. You just take the sharp of that. That will be a definition for nabla y with respect to x. Okay, so in other words, this star not only proves uniqueness but also proves existence. And let me just make a comment that this star is called the Koszul formula. Okay, so this proves the proposition. And then the Christoffel symbol expression also follows immediately. So the Christoffel symbol formula follows since the Lie bracket of any of these standard basis vector fields is 0. Right, so then you can apply the Koszul formula, and the reason why you have this inverse is precisely because you have the Koszul formula. In the end, you apply the sharp, and if you remember our discussion of the sharp operator is obtained by taking a one form and then multiplying it by the components of the inverse metric. So that is why this inverse sort of shows up. Okay. Alright, so I will leave it as an exercise for you to work out the details. So let me give you a couple of examples. So firstly on Rn, the trivial connection is in fact a Levi-Civita connection. Okay, so in fact it's easy to check that this is metric compatible. So remember, this was the trivial connection where you just take component wise derivatives, right? So this is a metric connection, and it's also, the torsion also vanishes, and this is basically Clairaut's theorem. So we study this theorem in multivariable calculus that mixed partial derivatives are equal if you have, let's say, a C2 function or something. So that basically implies that because our connection is just component wise differentiation, the Clairaut's theorem on mixed partials implies that the torsion will be 0. Okay, the second example is slightly more sophisticated. So suppose you take a Riemannian submanifold of another Riemannian manifold M tilde G tilde, and nabla tilde are the Levi-Civita connections. Okay, then my claim is the following: So remember in I think the previous lecture or maybe the lecture before this, before the previous lecture, I explained how suppose you have a connection on Rn and you have a submanifold of Rn that induces and if you have a projection map from the tangent space of Rn to the tangent space of M, that naturally induces a connection on M, right? And an especially important class is when you take orthogonal projections. So, so the point is that if you now have a Riemannian submanifold of another manifold, in this case M tilde G tilde, then in fact the Levi-Civita connection on M is precisely obtained by this construction. Okay, so the Levi-Civita connection is precisely the orthogonal projection composed with the Levi-Civita connection of the ambient manifold M tilde. Okay, now the proof uses a trick again that's common when dealing with Levi-Civita connection. So, so given xy vector fields on M, let x tilde y tilde be arbitrary extensions to vector fields on the ambient manifold M tilde, and we define dx y. By definition, this is precisely the derivative, covariant derivative computed in M tilde using this Levi-Civita connection, and then you orthogonally project it. So that means this d that I have introduced is precisely the orthogonal projection composed with nabla tilde. So what is the goal? The goal is to show that this d is the same as the Levi-Civita connection on M. Okay. So it's a good exercise to show the following, that d is metric compatible so this is because nabla tilde is metric compatible. So since nabla tilde is, and then you are using the orthogonal projection. So the orthogonal projection makes sure that even when you project it onto the tangent bundle, the resulting d is also metric compatible. This is a good exercise, you should try to write down the details. Similarly, d is also torsion free. Again, this is precisely because the nabla tilde is torsion free, and this uses the following fact that if you take the Lie bracket of x tilde y tilde and compute it at any point on M, then this is the same as the Lie bracket of xy. Okay. So that means as far as if you want to test for torsion freeness, this orthogonal projection really isn't necessary, because the Lie bracket of x tilde y tilde is the same as the Lie bracket of xy. Okay. So so it's a good exercise, try to work out that d is a metric connection and d is also torsion free, but this implies that d has to be the Levi-Civita connection, right, by definition. But then by the uniqueness of Levi-Civita connection, this implies that d has to be the same as nabla. Okay, so in other words, if again just to repeat myself, if you have a Riemannian submanifold of M tilde G tilde, then the Levi-Civita connection on M is given precisely by taking the Levi-Civita connection on M tilde and orthogonally projecting it onto the tangent space of M. Alright, so maybe let me end today's lecture with some nice properties of the Levi-Civita connection. So the first is what is called as naturality. Okay, so suppose phi is a local isometry. Okay, so then for all vector fields x tilde, y tilde on m tilde, if you take this covariant derivative and push it forward under this derivative map, then that is the same as calculating the covariant derivatives of the push forwards. Okay. And the second property is that if x and y are vector fields along a curve and dt of x is 0, dt of y is 0, so these vector fields are parallel, then it turns out that if you take the inner product of x of t and y of t, then that is actually a constant. So parallel transport with respect to this Levi-Civita connection actually preserves the inner product. So this means this map, parallel transport map, is an isometry. Okay. So of course this is parallel transport with respect to the Levi-Civita connection. So let me write down a proof. So let's first prove naturality. Okay, so because phi is a local isometry, so for x y in vector fields on M, let U be an open set where phi is an isometry. So let U be an sorry, let me do this again. Right, so you start with two vector fields on M. Let U be an open set and U tilde be an open set of M tilde such that phi from U tilde to U is an isometry. Okay. So then because this is an isometry, one can define x tilde to be the inverse image under the derivative map of x restricted to U. So this will now give you a vector field on U tilde. Similarly, y tilde will give you a vector field on U tilde. Right, and then we define dxy on U to simply be d phi of nabla tilde applied to x tilde and y tilde. So then as you vary your as you cover your manifold by these open sets, dx d will define a connection. Okay, and it's a well defined connection precisely because of these locality properties, right? The connection only sees the behavior of y on these open sets. Okay. Also, one can again check that D is a metric connection and is torsion free. So this implies that D has to be again the Levi-Civita connection on M, and hence by our construction of D we get the formula that or in other words d phi of this is equal to this. Okay. So again this trick is used often, that whenever we want to show that the Levi-Civita connection is a certain something, we show that that certain something also is a metric compatible connection and is torsion free, and hence it has to be the Levi-Civita connection, right. So we leverage this uniqueness again and again to show equalities of this type. And the second was to show that the parallel transport map is an isometry. Well, that's easy by the product rule, because what is d by dt of x of t comma y of t by metric compatibility, this is the same thing as dt of x comma y plus x comma dt of y, because this operator dt is essentially just the covariant derivative along this velocity vector of gamma, right. So so this operator dt will also satisfy the metric compatibility. Okay. But then because these are parallel vector fields, this is 0 and this is 0, so the net result is 0. So this shows that the parallel transport map actually preserves the inner product. It's an isometry of the tangent spaces. All right, so that's it for this lecture. Thank you for your attention, and I'll see you next in the next lecture.